Hi, this is John Whitaker again for the Mathematical Analysis 2 class. And this is our 24th video lecture. I thought last lecture we would get through with the series, but we didn't quite make it, but we'll definitely make it today. We ended last time talking about rearrangements of a series. And we had been looking at an example. I'd like to re-examine that example. So we had this sum as n runs from 1 to infinity of minus 1 to the n plus 1 over n. And of course that's equal to 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 and so forth. And a rearrangement of this series is 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 plus 1/13 plus 1/15 minus 1/8, and continue on. This, where what we're doing is we have two positive terms followed by a negative one, negative term, and that's the way we consistently go throughout this rearrangement of the above series. Now, we showed this series in this form is a convergent alternating series. Okay. The question here that we're going to have is, look, when we have this original series, it converges to something. Will the rearrangement converge to the same thing? And in finite, when we have finite sums, it doesn't matter the order in which we add things. But when we have infinite sums, it turns out it does matter. And this example illustrates this. So let's look at this rearrangement and the original series. Say some things about this. Okay, so first of all, let us let S be equal to the sum as n runs from 1 to infinity of minus 1 and n plus 1 over n, the original problem, the original series, I should say. Then S is equal to 1 plus 1/2 plus minus 1/2. Minus 1/2. Plus 1/3 plus the sum as n runs from 1 to infinity of minus 1 to the n all over n plus 3. Okay. Okay. Here's something to note, is that each of the partial sums for this particular series, the sum as n runs from 1 to infinity of minus 1 to the n over n plus 3 is negative. And thus, this sum what it converges to is less than 0. So what that tells us then, S is going to be less than, since this is a negative quantity, S is going to be less than just these first three terms. added together, subtracted. Okay, 1/2. Okay? And that ends up being 5/6. So we got S is less than 5/6. Now, we'll let S prime sub n be the nth partial sum of the rearrangement where we had 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4 plus 1/9 plus 1/11 minus 1/6 and so forth. That rearrangement. So S prime is the rearrangement. Okay. Now, these terms in the rearrangement can be grouped into threes having the form 1 over 4k minus 3 plus 1 over 4k minus 1 minus 1 over 2k. Okay? So if you list out those terms in the rearrangement, just say first 3, the next grouping of 3. This is what their terms look like. Okay? And this can be shown just using algebra that has to be greater than 0. So when you add 3 to the next one, next grouping of 3, you got something positive added, so it gets bigger. So what this says then is that S prime sub 3 is less than S prime sub 6, the partial sums for this rearrangement, the sixth partial sum, and then it was less than S prime 9, and so forth. So what we get is that the lim sup of the S prime sub n, we know this exists, the lim sup, that's got to be bigger than just S prime of 3, which is just the first 3 terms, okay? So the first 3 terms, that is 1 plus 1/3 minus 1/2, and that's equal to the 5/6. So the rearrangement cannot converge to the sum of the original series. Okay. It turns out the rearrangement does converge, but it doesn't converge the same thing. So this is an example. This is an example of where if you rewrite or reorder the terms in an infinite sum, you don't get the same answer. That's really contrary to what we expect. That is true. Okay. Theorem that I'm just going to state without proof is that if we let the sum of the A sub n's be a series of real numbers, talk about real numbers, which converge, but not absolutely. So they converge non-absolutely. We're also going to suppose that infinity is less than or equal to some number alpha, is less than or equal to some number beta, which is less than or equal to positive infinity. So you give me any two numbers, extended real numbers, okay? Then there exists a rearrangement we call it the sum of A sub n primes of the original series with partial sums. We'll define, or we'll denote by S prime of n, such that the lim n of, as n goes to infinity, of the S primes of n will be equal to A, and the lim sup of the nth partial sums of the rearrangement will be equal to B. Whoa, what's that telling us? So what that says, so implications of this theorem are one, if this series converges non-absolutely, then given any number, we can find a rearrangement of the series that converges to that number. Wow. Okay, so we get this series that converges non-absolutely, and then you give me any number, I can make a rearrangement of that original series that converges to that number. That's amazing. And then two, we can find rearrangements that don't converge. For a series that is that converges non-absolutely. Okay, so you give me some series that converges non-absolutely, and I can do a rearrangement of it, and it won't even converge. Okay, so we want to know, what conditions would imply that a rearrangement would converge to the same thing as the initial series. And so that's what the next theorem addresses. Says if this series A sub n is a series of complex numbers which converge absolutely, then every rearrangement of this series converges, and they all converge to the same sum. We will prove this. So it is absolute convergence that allows the rearrangements to converge to the same thing. Here's the proof. Let A sub n prime, which we can rewrite as the sum of A sub K sub n, be a rearrangement of the sum of A sub n's with partial sums A sub n prime. I'm sorry, S sub n prime is what we can call it. Given, excuse me, given epsilon greater than 0, there exists an integer, big N, such that for all n and m bigger than this big N, bigger than or equal to, we have the norm, as I go from m to n, of the norm of the A sub i's, that will be less than or equal to epsilon. And this is by the Cauchy criterion being applied to the absolute values of the sum of the absolute values of the A sub i's. And we know that this converges to the sum of the absolute values as I runs from 1 to infinity. Converges because the A sub i's, some of the A sub i's are absolutely convergent. So this is the Cauchy criterion applying that. So here, this outer norms isn't playing any role because these guys are just going to be sums of positive numbers. And so what we have is for all n greater than or equal to m greater than or equal to this big N, this sum is as I runs from m to n of the norms of the A sub I will be less than or equal to epsilon. Now what we do, we choose P such that the set of integers 1, 2, 3, all the way up to n, this big N, what we're working with. Okay? Are contained in the set case of 1, case of 2, case of P, which is forming the rearrangements. Okay, that's what we did. Then, if n is bigger than p, the numbers a sub 1, a sub 1, a sub 2, all the way up to a sub big N will cancel. And the difference S of n minus S of n prime. Okay, so this is the partial sum for the original statement of the series. This is the partial sum for the rearrangements. Thus, if you look at S of n minus S of n primes, the terms that are going to be added up in here are going to have indices for the a's, not a prime, but the a sub k's, and where the k's are going to be bigger than the n. And so I'll write this down here. This is the sum or difference. There could be some subtraction here. Of terms of a sub i's with i's being greater than or equal to n. And so that's less than or equal to the sum of the a sub i's in norms, okay, which is less than, of these terms, which is less than or equal to epsilon. Okay. Now, here's what I claim. I claim that the limit as n goes to infinity of S of n prime equals to the limit as n goes to infinity of S of n. So that's showing that the limit of the partial sums of the rearrangement is equal to the limit of the limit of the sequence of partial sums for the original statement. So let me say it again. So this shows that the limit of the sequence of partial sums for the rearrangement is, this is my claim that I showed, is equal to the limit of the sequence of partial sums for the original sequence. But we know that converges, okay? Okay, so here's the proof of claim. We'll do it on the other side. Proof of claim. Okay. Well, we know the limit as n goes to infinity of s of n exists. Let's call it s equal to the limit as n goes to infinity of s of n's. I know this exists because the original sequence converges, because it converges absolutely. Okay. Okay, so let epsilon be greater than 0 be given. Okay. Then we know that the s prime sub n minus the s, its norm, is going to be equal to s prime sub n minus s of n plus s of n minus s. So I just introduced this term from the sequence of partial sums from the original statement of the series. And that's going to be less than or equal to s of n prime minus s of n plus, so it's the norm of that quantity, plus the norm of s of n minus s. Okay. So there exists a natural number n such that for all n bigger than or equal to big N, s of n minus s will be less than epsilon over 4. That's because this sequence converges to s. By our previous work, for this proof, we were given epsilon greater than 0. We got some spot such that beyond that spot, we get the following. There exists a p that's a natural number. Such that the norm of s of n prime minus s of n will be less than epsilon over 4. And that's true for all n bigger than or equal to p. Okay, and so what we do we let big B maybe equal to the maximum of these two spots, N and P. So for all n bigger than or equal to b, is s of n prime minus s will be less than or equal to s of n prime minus, I'll write down s of b plus s of b minus s, and that's going to be less than or equal to epsilon over 4 plus epsilon over 4, which is less than epsilon. Less than or equal to here. Okay. And so that says that the limit as n goes to infinity of s prime sub n will be equal to Rs. And that's what we're wanting to show. That ends the work that I wanted to do for series. Now we're going to move on to chapter 7. For chapter 7, it's somewhat analogous to what we did in chapter 3, where we were talking about convergent, it's going to be based on convergent sequences. But instead of having sequences of number, we're going to be talking about sequences of functions. That's what chapter 7 deals with. So here it's sequences and series of functions. Okay, this is chapter 7. Okay, we're going to start off with the definition. Before that, let me say this. We will be considering complex value functions in this chapter. So as a definition, suppose f sub n is n runs from 1 to infinity, is a sequence of functions sequence of functions defined on the set E, so for each n they're defined on the set E. Okay. And suppose this series is in run from 1 to infinity of f sub n, sorry, not the series. Okay, and suppose the sequence of numbers, sorry, f sub n of x, n run from 1 to infinity, converges for each x in E. Okay? Then that allows us to define a function we'll define this function f of x equal to the limit as n goes to infinity of f sub n of x. Okay? And say that f sub n of x, or f sub n, I should say, as a sequence of functions, converges to the function f pointwise. Okay. On E. Okay. So that's the definition. In other words, another way of thinking this, we say in other words, the sequence of functions f sub n of x, or f sub n, converges pointwise to a function f on E if for each x in E given, so you take a look at it particularly, given epsilon greater than 0, there exists a natural number we'll say n. Remember this n that we pick, it can depend on x and it can depend on epsilon, such that for all n bigger than or equal to this big N, the absolute value of f sub n of x minus f of x will be less than epsilon. That's what it means for this sequence to converge to that number. Another definition, and we'll do examples of these definitions. Okay? Another definition is suppose f sub n, the sequence of f sub n, is a sequence of functions defined on a set E, okay, and suppose the series as n runs from 1 to infinity of f sub n of x converges for every x in E then we call the function f of x equal to the sum, as n runs from 1 to infinity, of f sub n of x. The sum function for the series f sub n. In the last two definitions, f, the function f of x, is called the limit function. Limit function. Okay. Just as a comment, we will be concerned with the discovery if properties functions f sub n will be inherited by the limit function f. Okay. For example, if the f sub n of x's are continuous on E is the limit function. Continuous on E. That's one thing. Okay, and then as another example, say if f sub n are differentiable, integrable, or integrable, will the sequence f prime of n converge to f prime, or the sequence of the integrals of f sub n, will they converge to the integral of f? So those are types of questions we'll be trying to find out. In general, these questions involve whether or not we can interchange limits. As example, when we talk about continuity of big F, so is the limit as t go to x of the limit function f of t. Okay? Well, that's really asking about the limit as t goes to x of the limit as n goes to infinity of f sub n of t's. Okay? And the question is that equal to the limit as n goes to infinity of the limit as t goes to x of s sub n of t? So this gives continuity at x. This is the answering question of continuity at x for each n. And when we take a look at that limit as n goes to infinity, do we get the same thing as taking the limit as n goes to infinity first and then looking at the continuity of that resulting function? Okay? So that's what we're being asked about. Okay, in general, often the answer is no. Is that we cannot interchange limits and get the same result. And what the book does, and what I'm going to do, is look at a few examples to illustrate this. let's look at this particular example. This is straight out of the book. So m is equal to 1, 2, 3 forever, and n is equal to 1, 2, 3 forever. Define S sub m comma n as m over m plus n. Okay? Now, for any fixed m, so if you fix n, then the limit as n goes to infinity of S sub m comma n will be equal to the limit as n goes to infinity of m over m plus n, which equals to 0 as n gets really big for a fixed m. And so the limit as m goes to infinity of the limit as n goes to infinity of S sub m comma n will be equal to the limit as m goes to infinity of 0, which equals to 0. However, for any fixed n, the limit as m goes to infinity of S sub m comma n will be equal to the limit as m goes to infinity of m over m plus n. And this is infinity over infinity. If you take the derivative top with respect to n, derivative bottom with respect to n, usually we'll get 1 over 1. And that's equal to 1. So the limit as n goes to infinity of the limit as m goes to infinity of S sub m comma n, that's going to be equal to the limit as n goes to infinity of 1, which equals just to 1. So we can see here that interchanging the limits does not yield the same result. Let's look at another example. Okay. Let's let f sub n be defined from 0 to 1. And f sub n of x, this is from 0 to 1 into R, and, or I. F sub n of x is equal to x to the n. Okay? Okay. Okay. So what does this look like? It starts off at 0. Well, when we look at this is 0, this is 1 here, here's 1. When we look at f sub 1, that's just going to be x to the first. It looks like a straight line. F sub 2 is going to be x squared. That looks like this. X cubed is going to be, F sub 3 is going to be x cubed. That looks like this. Okay? And they keep doing this in this pattern. Okay, here's also. Note, F sub n of x is continuous on 0 to 1 for each n. Now, for each fixed x, and, well, I'm going to look at 0 up to 1, but not including 1. The limit, as n goes to infinity, of f sub n of x will be equal to the limit, as n goes to infinity, of x sub n, and that's going to be equal to 0 for any number in between 0 and 1, including 0 but not 1. But if you take 0, which is obvious, 0 to any power is going to be 0. You take something like a half, take a half and start raising it to bigger and bigger powers. So it keeps getting smaller and it goes towards zero. Okay. Note the limit as n goes to infinity of f sub n of 1. Well, that's just equal as limit. That's equal to the limit as n goes to infinity. Well, we're replacing x by 1, and so we get 1 to the n, and that's just 1. So, this means that our sequence of f sub n's converge pointwise to f equaling, so f of x equaling, it's equaling to 0 if x is an element of 0 to 1, but not including 1, and 1 if x equals to 1. Right? And so, this is an example. Okay, this is an example of a sequence of functions each of which, each function being continuous but converging pointwise to a non-continuous function. Because this function here, f, what it converges to, it looks like 0 up to 1, and then f1 at that spot. All right, ladies and gentlemen, so that shows that pointwise convergence doesn't give us kind of a nice property inherited by the function, the limit function. And so we'd like for that type of property to be inherited, and maybe we can find some criterion that can give us that. And we'll work on that and eventually get to it. Okay, but that's enough for today. Thank you very much.